Okay, so in this next one, we want to find there's a cam follower mechanism, and has this ball inside this like little slot, and it's held onto the surface as a with a spring, and the shape of the cam is determined to be this right here, this equation. R is equal to 1 plus 0.25 cosine 5 theta plus, oh, it should be minus. I'm sorry, I made a mistake there. There, it should be minus. Whoop, fixed it. Okay. Minus pi over 2, and that creates a star. And it does, in fact, create a star, and I'll show that in a second. Where r and theta are expressed in inches and radians, respectively. And the polar position, right? So I mean the angular position of this thing. So theta is programmed in a computer that's controlling a motor or something that's turning the thing, as theta is equal to 2 over pi times sine of pi t, right? Where theta and t are expressed in radians and seconds, respectively. Now, we want to find when it's in the position of theta is equal to 30 degrees, we want to find the velocity in polar coordinates, and then the velocity in rectangular coordinates, and then the acceleration in polar coordinates and the acceleration in rectangular coordinates. I tried to create this problem as one that would be maybe something that could be possibly real, and one that requires you to do some stuff in polar coordinates. That's it's kind of typical. Since we're only doing, this is a Tuesday Thursday problem, right? A problem that's due on Thursday, only giving you 2 problems for this homework in homework 5. It'd really be kind of better if there was 3 problems or even more, so that you get an opportunity to try the various kinds that kind of, so you could kind of have experience testing them through. So be sure when preparing for an exam that you work through some of the other polar example problems, right? Because there are some that kind of like have certain features to them, and this is one I tried to make that has some of the most common features there. So let's see. One thing. Okay, I was thinking of trying to make this like Patrick Star from SpongeBob, but if you're not familiar with SpongeBob SquarePants, then I feel sorry for you. Your childhood, you missed out. But we could even draw Patrick on there, right? We could draw him. We could put his shorts onto this and have him big, this big smile right there. Right there. There's Patrick Star right there. But let's go to Excel and take a look real quick at sort of like a little proof that this is actually a star. So the best way that I know to kind of demonstrate this is, let's take this theta right here and make that from increments of, I think I want 5 degrees, right? So I'm going to go increments of 5 degrees, and we want to get to 360, right? So I'm going to drag this down until we get to, it's probably somewhere in there. No, I gotta do more. All right. There you go, 360. 360, okay. And here we're going to set that equation that we just had right there. So that equation was 1 plus 0.25 times the cosine of 5 times, of course, but in Excel these always need to be in radians, and I made them in degrees over there. So I'll go radians, whoop, I said plus, I meant times radians of this right there, right? And then minus pi, gotta close that, divided by 2, which is like 90 degrees, right? And did I do that right? I think so. We'll see here in a second. I'll double click on this. Now I'm going to plot this, and the best way to do that is to turn this back into x and y, right? So I take this right here, which is really the r value, and I multiply it by the cosine, but I need of this angle, but of course it needs to be in radians again, so radians. I wish Excel had an alternate like cosine and sine that would just do degrees, because I've probably written out radians 1,000 times in my life. Boom. All right, and then you're going to say equals to this times sine. Of course, got to turn this into radians. Radians, boom, boom, and close it in. All right, so these two, we can go ahead and it goes all the way down, right? But now I can plot this, right? So I actually already have it highlighted. I'm going to plot this. Boom. Check them out. We'll get rid of this, and we'll see if we can make it like even. Like we can make this. Yeah, it goes. Yeah, there you go. There's the star. See, it actually does make a star. And something we might want to do here is take a look at this point right there at 30 degrees. So I could just plot that, right? So I could take this and I could select data, and I can add a new thing, and I'm just going to plot that point. So x, the x coordinate, and then the y coordinate, 30 degrees right there. Boom. And of course it doesn't show up yet because it does not, it's only looking at lines. So I'm going to take this, and there it is right there. And if I wanted to, I could come into here and make a marker out of that. So marker options and make it built in. So right there, that's the point that we're looking at. We can expect that the velocity is going to be tangent to this at this location right there. So kind of point, it looks like it's kind of coming up on a slope right there. We might consider, actually, I only used 5 degrees. We could actually go like a little crazy and make it like 1 degree increments, or even just 2.5 degree increments. But anyway, you could. This is. I just wanted to point out that this is, something that's real. All right, so here we go. Here's the procedure that we want to do. Our first goal, is to get the variables of interest, and then we can plug them into the forms that we know, right? We know that the velocity in polar coordinates is going to be r dot times er plus r theta dot e theta. And then the acceleration is going to be a longer one, where it's going to be r double dot minus r theta dot squared er plus r times theta double dot plus 2 r dot theta dot e theta, right? That's the form. So the variables of interest that we want to find, right? So I'll say first find VOI, the variables of interest, which are r dot, r double dot, theta, theta dot, and theta double dot. Okay, so those are the variables of interest, and that's what we have to find. If we look back at this problem right here, we're given an angle. Of course, this is in degrees. Everything else uses radians, but this one happens to be in degrees. And if you convert this into radians, right, the best way to do that is to take 30 degrees, divide it by 180, and multiply it by pi, right? So we end up knowing that that's pi over 6 is going to be that in there. So the first thing that I'll do, let's see if I going to get this right here. I can take, one thing I want to do is make sure my calculator, and here my handy dandy calculator, I want to turn this, in this case, turn it into radians. Got to remember to turn it back when we use it later right there, right? So what we could do is say if pi over 6 is equal to 2 over pi sine of pi t, right? Then the time we find right here, so we can divide this by 2, multiply it by pi, take the inverse sine of this side, and then with that, whatever that is going to be equal to pi times t. We can solve for the time, all right? So I'll demonstrate, just pi divided by 6, right? Then divide it by 2 and multiply it by pi, right? Take the inverse sine, a sine, and then divide by pi. And we should get, this is going to occur, so it's going to reach 30 degrees at 0.3074. I should mention it's going to reach it the first time, right? Because actually it has a good chance of cycling back and forth. If we were to take a look at this right here, I think I'm pretty sure because of that pi right there, that's going to be like the period right there, right? So whatever we find, we could find the time that it's going to come up. It's going to come back and forth between positive and negative. I think it's only going to move about, it's going to, when it goes to 180 degrees, right? So each time increment, yeah, something along those lines. Yeah, it's going to move back and forth. Right? I'm going to stop trying to anticipate what the range is. But yeah, this is the first time that it goes, if it's moving in a counterclockwise direction, which we anticipate that it will. All right, so what we want to do first might be, we could do either one of these first, but we will quickly find that we're going to need to get a theta dot at some point. So let's just take the derivative of the theta with respect to time. So I'll write these out, right? So here's the VOI. I'm going a little slower than I should. Theta is equal to 2 over pi times the sine of theta times t. We already know the answer to that. That's going to be pi over 6, right? Or I think I wrote it out somewhere, what pi over 6 turns out to be. 0.5236 radians. We don't really need that at this point, but maybe for something. All right, so theta dot here is just going to be the derivative of this. Well, the derivative of the sine is going to be a cosine, and we're going to take the pi to the outside, going to multiply it, so that pi right on the outside goes away, so you get 2 times cosine of pi times t, and we already know what the time is going to be, right? So I could plug this back in. I don't have to show you plugging it back in. We plug in right there. Maybe I'll just do that. I'll do it right now. Pi times 0.3074. Make sure this is in radians, and we get that this is 1.138 radians per second. To go double dot, right? So we're going to take the derivative of this again, and pi is once again going to come out to the outside. But now the derivative of cosine is a negative sign, so we get a negative 2 pi sine of pi t. And if we plug those numbers in, oh, I didn't need a sine of pi times 0.3074, we get a negative 5.168 radians per second squared. Okay, so we know that the thing is going counterclockwise, excuse me, but it's slowing down, right? So this thing is rotating, but it's not rotating as fast as it was before. And that's just controlled by a motor. But now let's go to the radius right here. Okay, so maybe I want to give myself a little bit of room over here. So the radius is 1 plus 0.25 cosine of 5 theta plus, oh, I did it again, or plus, should be minus. By the way, that plus and minus, that just rotated the thing, right? That's all that this thing was there to do. I originally had it as plus. Here I can show you what I mean here. So like if I instead here went plus and fix it all the way down, you can see that it's rotated over. And I didn't like the direction it was going. And it's upside down really in there, right? So I'm just really kind of rotating it by 90 degrees. And so you can see, boom, there you go. Kind of looks cool, doesn't it? Kind of fun. Okay, so yeah, put that thing back as negative. Good. So put him back into place, and then I just have to put in my what that value was, right? This 0.5236, which is really 30 degrees. Plug that in. You don't need to see me do that. I get 1.125 inches, and we can even just see that over here, right? So at 30 degrees, 1.125. Great. Now becomes some tricky stuff. We want to take the time derivative of this. And maybe we did an example in class, but you got to remember, you take the derivative of this with respect to time, but this is a function of angle, not a function of time. To get around that, you use the chain rule. I'll write it over to the side, say, recall chain rule. If you take the derivative of the thing, I wrote this somewhere, if you take the derivative of something that's a function of that's actually a function of position, what you need to do is multiply it by d theta dt, right? If you're going to go d whatever times d theta, right? So I actually want to take the derivative of this with respect to position, with respect to angle, right? Because that's the function of angle, but I, ultimately want it as a function of time. So by multiplying it by this, I'm able to get around that. I hope that makes sense. So first, I take the derivative of this with respect to time is 0. 0.25. I'll just leave him out there. So I'm going to take the derivative of this with respect to theta first, right? And that's going to make a negative sign. So I'm going to put a negative out there. And I'm also going to need the 5 is going to come out. And I need that theta. This is going to be theta dot. So there's actually a theta dot that's placed in there because of the necessity to do this chain rule. And then it's sine, and then it just remains whatever on the inside. I hope that's clear. It's a kind of a trick. It's a way to get around the fact that this is a function of theta, but we want to take the derivative with respect to time. So we're able to do that because of the chain rule, because you see those two things will cancel out and functionally get there by multiplying it there. I don't want to waste up the page space by shoving the numbers inside there, but I put in the theta that I know, which is going to be, once again, pi over 6. The theta dot that I got from up here, right? So I guess I'm going to be lazy. Okay, negative 1.232 inches per second, and that's r dot, and we got to try to think, does that make sense? We'll take a look here. If we're thinking this is the position we're talking about, we can imagine as it's coming over here, it is getting shorter, right? So it's getting the radius is moving towards the center, so that makes sense that r dot is a negative, right? Always good to try to work those out, right? Whether something is makes physical sense. The next one, now this one becomes a really long one, right? So I'm not going to say I would be surprised, but it's a challenging thing. You got to remember that this thing does change with respect to time. So you have to take the derivative of this multiplied by the original, and then take this times the derivative of that, right? Because there's two separate things. So you have to use the product rule as well here. So I'm not sure which one I wrote out first. I think I wrote, I think I did this one first, but maybe it would make more sense. And I didn't bother figuring out what that number is. I just left it for the ride. But if I do this one first right here, it's the derivative of the sine is this going to be the cosine, right? So it's still going to be negative here, 0.255 squared, right? Because that 5 is going to come out again. I have to do that same thing where I have to multiply it by theta dot. So it's going to be theta dot squared cosine of 5 theta minus pi over 2. Right? But I'm not done because I've only taken the derivative of this. I also have to take the derivative of that. So it's everything here and then that theta double dot. 5, and now that becomes theta double dot, and this is sine of 5 theta minus pi over 2. And this is one of the reasons why we take calculus, right? Is to be able to understand, there's not why you would have to do this. So I'm not going to reteach calculus, but it is something we want to have. And then I'm not going to rewrite all the stuff in there. I'm just going to walk through and plug the numbers in. Maybe that's kind of a bad example, but I'm going to do it this time anyway. I end up getting a negative 2.50 inches per second squared. All right, so now I can find all of these things. I can plug these back into those main equations and find my velocity is going to be, well, this first the negative 1.232 with the r dot, so that's this, and then this is going to be r, which we found to be 1.125 times my theta dot, which we got to be 1.138 e theta. So that's going to be equal to, we'll write this out as negative 1.232 ER plus 1.283 E theta. And this should be inches per second in there. So that's part of the first problem of part A of this. I know it's a long problem. I wanted you to get a lot of experience in here. All right, so so let's write out the this one. So we're going to plug back into this equation right here. So the r double dot ends up being negative 2.5. I'm going to subtract out our 1.125 times our, where did we go right here? This squared, right? Theta dot squared. Let's see, I can't get it all on one page. See, I'll keep going up. There we go. So I can have this and I can reference it back and forth up there. Yeah. So there it goes. That's the one we're going for. And 1.138 squared as ER plus, now we're going to go R. So R is 1.125. Theta double dot is a negative 5.168. All right, and we're going to add 2 times R dot, which is a negative 1.232 times theta dot. And remember that this part right here is the Coriolis kind of acceleration type of thing, and we'll keep hitting home on that, especially if and when we get to rigid body kinematics and we have more Coriolis acceleration stuff. Where was I? Theta dot 1.138, and then we have E theta, and these are inches per second squared. And then I do the math out. And this will be the answer to part C, I think, of this, right? I asked for acceleration in terms of polar coordinates. So we get a negative 3.957 if I did the math right, and there's nobody saying that I did. And then this one is going to be negative 8.618 E theta inches per second squared. Now I want to do the coordinate transformation thing. This will be more practice for the coordinate transformation. I don't know if I want to go to a new page yet. Let me take a look here. Okay, so we can set up the array here on this page. Here's my I and J. So we want to get this into I and J. And we're going to have ER is that orientation. Here's the angle. Whoops. Sorry about that. And let me draw this one up here, perpendicular to it. Oops. And this is the E theta. Of course, that's the theta right there. And this is really similar, maybe even identical to some of the other ones that we've done. So I almost kind of wish we had made more of a little bit of a weirder one so you would have seen it. But anyway, here's so the coordinate transformation array looks like, I don't know, let's see here. That one, I'll go two grid things. Nah, I didn't make that nice and even there, did I? Something like that. And then here's somewhere in the middle. Okay. And there's our I and J. And here's our ER and E theta. Right, and so ER is just going to be positive cosine with the I. And positive sine for the J. E theta is going to be negative sine. And then positive cosine. Right in there, right? And go to a new sheet. This is page 3. I'm Dr. Deal. It's the fall of 21. We're in ES1, 10. We went back to statics there for a second. We went to 11. And this is homework 5 already. And this is problem 2, continued. ... Okay, so we take the velocity here, and we have 2 parts to it right here, right? We have this part and that part. So applying our coordinate transformation here, we say I'm gonna do everything in the I direction first, and focus. Negative 1.232 times the cosine, right? We're taking ER right here, right? So we'd have the ER, so times there, then we're going to take the E theta and multiply it by there, right? So that's the cosine of 30 degrees. I'm going to make sure I put my calculator back into degrees when I get to this point right here, if I'm going to use that. And then we'll add to that this guy times him, right? There's both of the I parts, right? So we'll have 1.283 times the negative sine of 30 I, and then I had negative 1.232 times the positive sine of 30. I'm going to run out of room again. Plus our 1.283 times the cosine of 30. J. And so where'd we go? Where's my values? Negative 1.708 I, if I did the math right, and there's no saying that I did. 4951 J inches per second. Now, something that would be a really good idea right here, especially if you want to try to get the bonus, is to find the magnitude and direction of the velocity, right? So we take the square root of 1.708 squared, so this can be the speed, right? And 4951 squared, and I end up getting 1.779 inches per second. We can also find what the angle is right here, and I'll say that the angle of the velocity is going to be the inverse tangent of our rise over run, or point, should be a 4. I could try to make that 9 into a 4, but it didn't make a very good looking 4. So 4951 divided by 1.708, and I end up getting 16.17 degrees. Now, this wasn't asked for, but what it can do is that could kind of like give us a sanity check. Yeah, I could believe that that was going to be, you know, if I really zoomed in onto that spot. And once again, we might want to make this a finer, discretized thing. Like, you see, these are the points that are on this thing, or maybe they're not. Let me double check. Like, we could do this right here. Let's just go 1, 2, 3, 4, right? So this is not going to be all of these, but let's see. Boom, right there. And this point right here is not being plotted correctly now. We'd have to go all the way down to here, right to there and there, right? So that's the point. And that kind of gives us maybe a little bit of a better idea of what this, we were looking for the tangent to see if we believe that that angle is going to be correct right there, right? And of course, that's only plotting part of it, but that's got a lot more points to it. Anyway, that's the reason why I did it. It's like a sanity check. The acceleration here now, we want to do the pretty much identical thing here. We're going to take this acceleration. Can I get that on the same time? Yeah. Oh, I can cover this up, right? That's what I can do. If you go, the acceleration here is going to be negative 3.957 times the cosine of 30 degrees, all right, plus negative 8.618 times the, I almost did that wrong. No, that's correct. This can be I, yeah. Negative sine of 30 degrees. I. There's not enough room here, so I'm going to go down over here and then go negative 3.957 times the sine of 30 degrees plus negative 8.618 times the cosine of 30 degrees. J. And these are inches per second squared. And what we get for an acceleration now is 0.8821 I. That is if I did this correctly. And a negative 9.442 J. Inches per second squared. And if I want to write out the answers, boom, boom. Velocity is equal in polar coordinates negative 1.232 ER plus 1.283, and a lot of times maybe I haven't been consistent in this. I will go down to 3 sig figs as part of the answer. And the velocity is now going to be negative 1.708 I plus 0.4951 J inches per second. C, acceleration is equal to negative 3.96. There we go. Decided 3 sig figs. Save myself an instant. 6.2. Whoop, lazy. And that's inches per second squared. And then lastly, D, the acceleration is 0.882 I plus negative 9.44 J inches per second squared. And there is part E that you could do if you'd like. And I ask you for the radius of curvature at this location. I'm not 100% sure I got this. I did it. I'm not going to show it to you. I want you to try to figure it out. Well, let's see. Let's grab a hold of that point again. Let's see. There it is. There's that point. I'm going to try to figure out what the radius of curvature is going to be. I didn't like the answer I got. I got only 0.359, something like that. And I'm looking at this and I'm going, does that seem reasonable? Because I think looking at, I'm just taking the whole, looking up the thing there. How big of a, maybe if I take this right here, you can't see my hand what I'm doing, but I'm kind of like holding my hand up to the screen and then using it holding it at like 0.35 and kind of seeing if I could, maybe kind of use it kind of like as a compass to kind of see. I don't know. But anyway, how do you think you would go about doing that? That's the question, how would you find? Do you know something special about radius of curvature? Here, I'll just go ahead and tell you how to do it. I bet none of you will actually do it. That's what I'd like to see. I'd like to see somebody that's got like enough to care enough to show me that they would actually do it. So I'll tell you how you do it. Right? Well, right here, that component. No. I'm sorry. What do you have to do? Skipped a step. You need to do a coordinate transformation to get it into tangential and normal components, right? Well, the angle right here, right? Because the tangential is going to be aligned with the velocity. So now you get like the normal is pointing inwards. So now you have a new coordinate transformation array that you can create. And now you can take the acceleration, probably going to be the easiest to do the rectangular one, and take the rectangular one and turn it into normal and tangential components, or tangential and normal components. And then the normal component of the acceleration is going to be equal to v squared over rho, right? Radius of curvature. So now you can find the radius of curvature because the velocity, I should say the speed. The speed, right? We have the speed here, and so you take that squared, and now you divide it by the normal component. Let's see if anybody will do that. It was going to be part of the homework, but then I said that's going to be way too long, and this is already way too long of a problem. It's already like 39 minutes. I want to see if any of you will actually do it. I dare you. I double dog dare you. Patrick Starr double dog dares you. That's what I'm saying. I hope everybody has a good Labor Day, and I hope you're not laboring too hard on dynamics on Labor Day. But I noticed that from the YouTube video viewed count that no one's viewed any of the videos yet for homework 4 on Friday. But that's okay. Hey, you got the weekend, right? Why do today what you could do, procrastinate until later? It's the engineer's credo. And you guys are engineers, so there you go. Have a great weekend.